Yeah, I want to share screen.
Whiteboard. How about that? Sure. Try to find this. A lot better.
This is much better.
Undo. You can undo. Here.
Yes, Control Z works. I love this. Okay. Okay, so this doesn't work so well.
Can you here,
Yeah.
if you get a chance to join the room as well, see if you can actually join the class.
Right. Okay, this is fine.
So or no?
Yes.
Okay.
New share. Oh shit. Portion of screen. Content from second camera.
I can see, by the way.
Okay. Share.
No.
Oh shit.
But like, you don't want to postpone anything, right? Because otherwise you're gonna have to deal with one movie and another problem set at the same time. Depends on what you're going to deal with, right?
Okay, I'm definitely going to try to fix the mouse because I'll need to use the mouse quite a bit. Additional mouse option.
Do we need it at all?
Yeah, we need a mouse for sure.
Later after this.
Okay, so Nicholas, where is the beginner's guide folder on your thing? Sorry, maybe I should just switch accounts to the beginner's guide account. Okay. Yes, there we go. Okay. Present.
You make the form, Shishir.
Yeah.
So I'm going to get rid of this Google Keep. Leave. And then what I'll do is if I want to use the whiteboard, I'll just share the whiteboard. Okay, and I'll write whatever stuff I need to down.
When you want
Yeah. Yeah.
You can just yes, just do whatever you do.
I'm going to be so weird.
Question? You have one? What are you doing for it's too dark.
How can you apply physics to minimize your exposure?
Too dark as well. I don't want to do the COVID one. What do you? I would just write, what are your plans for the week?
What is milk pulp?
No, come on. Just write something.
Like what milk or pulpy? Like orange juice?
Yeah.
That would be disgusting.
Exactly, right?
I mean, it would increase your dietary fiber intake. That would be good for you, but
What's the quote of the day?
it's in the drive. I mean, you can pick one.
So wait, what are you seeing? Is anyone else on the Zoom?
The quote should not.
Is anyone else on the Zoom call?
The quote is
Okay. Okay.
It's in the
Text. Quote.
I mean, like, actually, just right. And you know, you're actually right. That's why.
Can you open up your
Yeah.
lecture notes?
No. Well, I can, but. Okay, I'm gonna. Shishir, you should get used to using Nicholas's laptop too, because we don't want like too much downtime. No, with the back side of the touchpad. It's working okay. It's a little bit janky, but basically you should have all the slides in like physical form if you can.
Yeah, I'm trying. But I'll set them to skip slide.
We'll have like 17 more minutes.
7 more minutes, you mean?
Well, no, perfect.
Oh yeah, true, but we should head to Campbell at some point, right? And then we have to set up. That is true, yeah. But familiarity breeds contempt. Okay, that wasn't strictly relevant, but pretty sure they are. Alas.
Wow, I can't wait for general relativity pressure and quantum mechanics online.
How was their behavior?
They're doing well. Very well indeed. How do I know? Because were you there at that SPS? No, Shishir wasn't there, that's why. Shishir wasn't there.
I showed up now yesterday and we bonded over mutual admiration.
What? How do you know Nas? Oh. Okay, wait, so. Which way does this scroll? Select.
Yeah, he does. When is my lecture? The very end, if it even happens. Yeah, I joined this Zoom. Or Zoom on my phone. Yeah, I do. Did you make a yell key?
Yeah. What's the question?
if you transfer them or something. I don't know.
I feel like it was standing.
Something about toilet paper.
So wait, HR diagram, astrometry. Oh, hey, did we just start this meeting? This is interesting. I have no idea what's going on right now. Let's see. Oh, Nicholas, you might want to
Hello?
go on mute or something. So
I will mute, but does this work? Yes.
Hold on.
It's muted. Unmuted.
Okay. Post attendee. Sorry. I'm gonna stop this share. Is this the same meeting? Who that is on BGU?
What?
Is this the same meeting that's on BGU?
Yeah, it is. I clicked on the link. I clicked on the link that you sent out.
Okay.
Let me know. Look, we gotta.
Okay, so she's here.
Gotta do that.
Can you
Are you willing to do it like a hug?
Are you willing to do it?
Yes. I'm willing to do it after this.
I need
but
to
I'll
be able
just
to
do it.
see.
I'll just
Mute
have some loose ends and then we can
no audio.
do it.
What's
I
going
can
on
fucking do it.
from
I'm gonna be
the server side? And I need to go see else.
I'm not gonna sneak it. Can I sit like next to you?
But I'm gonna be using this laptop for everything else, right?
You know, you're allowed, so technically, I'm not allowed to be in there. It's no more illegal if you're in there. So it doesn't matter.
Okay.
I'm technically not allowed to be there without a
Could I get,
you guys see how, like,
could I?
can I see that next to me?
And so it's gonna speed back.
If the audio is off, it shouldn't. And it should be muted as well. Right? Thank you.
No, it will still feed back. No, even if it's muted. If it's muted, it won't feed back. No, it will feed back because what's happening is the sound will.
Oh yeah,
even if
you
it's
muted. Muted isn't like your phone.
Oh yeah. Okay. Well, it is now. Yeah.
Are we doing here? Or are we going to campus?
Here is fine. Okay. Did you make the form? Just put anything.
Can I write, Shashank? Your handwriting is a bit. I've already written.
How do you guys have different handwriting?
Okay, can I get the notes on that laptop next to me? And then ideally, Nicholas, if I can, on any other device, see what's going on, like from the client
I
side.
can't make it. You can't do it. Yeah, no, I can't.
Actually, then I'll just use my laptop.
I mean, it's fine. Like,
No.
it's not gonna feed back.
Yeah, okay.
That's fine. It's fine. Use this to figure out what's going on.
Testing. Test. Can you get rid of like the bottom? Can you full screen? Like present mode or something. No, this is the most presentable present mode. Because it's a Google Slides. Should I download it? I can't read it. Oh shit.
Use it to calibrate whatever you want. Know that there's a time delay whenever you're saying.
Okay, wait. It locked your phone. So maybe I should do this on my phone actually. That I can.
This is for me to watch. I can't fucking see it.
So can I show my video as well while I'm doing this? Yes. Okay, can I download these?
Yeah. The question is, what are you doing?
What? Me?
What are you planning to do?
Just watch.
No, like the question. Yeah.
Oh, I see.
They're gonna.
Okay.
Are you muted?
I mean, people can hear me through your.
Sure.
Why can't I start videos? Video. Meetings.
I can raise my hand. I raise my hand.
Hide non-video.
We're hopefully going to use the
Yeah, there's a lot of like.
Okay.
we decided.
Hello. This is Daddy on it.
Here.
Wait, do you have any space on your laptop, Nicholas?
Are you watching it right now?
To record the lecture. I accidentally did already.
What's it on?
I mean, yeah. Do it from cloud?
Mhm.
This is the-
That's fine, right?
Share
How
screen.
are you?
Oh my gosh.
Okay. So no one has filled out. Okay. We need to go to. Where's paint?
Okay, hold on.
So using OneNote?
I'm going to.
Are you ready for your lecture?
We go to OneNote and write down the key.
I can figure out. Probably will be.
Chunk.
No,
Paint.
forget about OneNote.
What?
What we're gonna do is new share whiteboard. Share. Okay, so that should. You can use text. Hold on. Just type it. Right. Hi to everyone tuning in. Can everyone hear me? If you know how to send a thumbs up, you can go ahead and do that. Who's on here? Wow. Awesome. And we want to turn the audio on. Yeah, I think people did, yeah. All right, so we're gonna start this soon. I have absolutely no idea how to use Zoom, and neither does my brother, but we'll figure it out. We'll figure it out.
So please put up. Yeah. More than 3 people.
I really need an extended desktop screen here. That would be like nice. Can I get the notes up on here?
Yeah.
And
You want it up?
I forgot. I also.
Okay, so if your access Zoom is in the same room, you should turn off your
Yeah,
audio.
yeah, we'll do it. I mean, I think you just make it.
Turn the audio on, reduce the sound.
No.
Okay.
improved gain follower.
What the fuck?
What? What happened? Who's joining?
Wait, what?
I had to. Wait, did you see that meme, Nicholas? We all talk about that. It was hilarious.
Wait, you can turn off your audio.
Oh, it's my audio. I think it's coming in through that. Right?
No, your video and audio is off.
My video is on, yeah.
But your audio is off.
Your audio is on, yes. Okay.
Damn, I just.
And what?
Yeah, because I think.
Okay, hold on. How much time do we have? All right, just give me 1 second. Let me.
Are you sharing your screen?
Yes, I'm sharing the. Hi, everyone tuning in to our online lecture. I have no idea how Zoom works, so I'm trying to figure it out. But while we figure this out, just bear with us. So does everyone know how to use the thumbs up feature? Can you thumbs me up?
Or thumbs up.
Oh, I saw Yonna, I saw Evan, I saw Imanol. Akshit. Thanks, Evan.
All right. So assuming people can do what I'm saying, please fill out the attendance. We still don't have nearly as many attendance forms as we do. Looks like people are very uncertain about the future. It's okay. Before we start, I'd like to say a couple of words about like the whole situation of like COVID and all. Stay safe. All right, with that, let's begin the astronomy lecture.
Yeah, and so again, if you guys are just coming in, go ahead and give me a thumbs up on Zoom if you can hear me. Okay, and so we're gonna try to make this lecture interactive. Try being the key word here. So, but we'll see how that goes. All right.
And we should note that now, like participation is going to like how we monitor your participation, which, as you'll remember, is like the bulk of your grade, is going to have to evolve slightly. So, and we'll try to get participation working on Zoom. But if that's not working out, then we might have to switch to some sort of like after, like a quiz or something after to like make sure you were like attending, present and stuff. So we'll see how that works out. Don't worry, if you're present, you'll be fine.
Yep, and so
let's start. So
I'm gonna try to put this where you can see us. All right, so I'm if you wanna have a look at video, We're gonna try to keep the video on my account, and then on the beginner's guide account, we're gonna have a screen share. So let's give that a try. All right, but let's get started. So today's lecture, I was really looking forward to giving because this is our favorite topic, especially me and Shishir. Oh yes, Yonna has also given us snacks. Thanks. All right, so this is our favorite topic, astronomy and astrophysics. This is, if you all know, this is what we do our research in, and perhaps during discussion, we might be able to talk about our research in greater depth. But just yeah, this is an awesome and fascinating topic, and some of you might have been waiting quite a while for this lecture. So we'll see how it goes. Astronomy and astrophysics. So today's quote, first of all: space is big. You won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the road to the chemists, but that's just peanuts to space. All right, and
So I want to start with how far everything is in space. So our planet Earth is around 13,000 kilometers in diameter. And you might have seen like pictures and models of the solar system before that show like the sun and like all of the other planets. I'm here to tell you that those are like often horribly off. Like there's no way they come close to delivering like the actual sense of scale of the solar system and like everything beyond the solar system. So in order to give you an intuitive idea, let's use an analogy here. Let's say we take, so as I said, the Earth is 13,000 kilometers in diameter. Let's say you take the Earth and scale it down to the size of a basketball. So in our world, when the Earth is the size of a basketball, the moon would be about 23.5 meters away. If you can visualize the Campbell Hall in your mind, like the length of the building is about how far away the moon would be if the Earth was a basketball, and the sun would be 9 kilometers away, somewhere near the Bay Bridge. And the sun would be the size of the Campanile Tower. So imagine a basketball next to the Campanile Tower. And that gives you an idea of the difference in size between the sun and the Earth. The sun itself is really huge, and it's also really far away. So astronomers quickly have learned that using kilometers for distances this large is just unwieldy. The distances are like, the numbers become too big, and it's just not a good unit to use. So we have to switch to another kind of unit. So astronomers use two units. Sometimes when we're talking about scales like distances, we use light years. So light years is the amount of time it takes for light to travel in 1 year, right? Another unit that astronomers use more often is parsecs, and we'll cover that slightly later. But let's start with light years because it allows you to get a good sense of scale of size. So we've discussed the speed of light before. The sun is so far away that it takes the light that's traveling from the sun about 8 minutes to reach the Earth. And so you're always looking at the sun as it was 8 minutes ago. And so we'll get used to the idea of things that you're looking at that are farther and farther away. Because they're far away, it takes light time to travel to us, and so therefore you're looking at them as they were slightly in the past. So it takes about 11 hours for light to go from one end of the solar system to the other end of the solar system. So the length of the solar system is about 11 light hours long. Now the nearest other star to our sun is called Alpha Centauri. It's the Alpha Centauri system. That's a full 4 light years away. So we always look at even the closest star to us, we're looking at it as it were 4 years ago, always. And we live in the Milky Way Galaxy. there are billions and billions of stars in the Milky Way Galaxy, and all of them are spaced apart by like more than like 4 light years from their neighbors. So the galaxy is actually mostly empty space, and so this is kind of unintuitive to think about. Let me can you switch the slide real quick? So this is an example of a galaxy. It's not the Milky Way Galaxy. It's actually another galaxy, but the Milky Way might look something like this. And so also, if you guys we haven't really been talking much about what we do in our free time and stuff, but one of the things Shishir and I do in our free time a lot is to take pictures of stuff in space. So the astronomy lecture is sort of where we just throw all of our pictures that we take onto a slide deck and just like share that with you. So this is actually, we took this picture with our own telescope, and it's of the Whirlpool Galaxy M51.
This one right here?
Yes. Yeah.
You took this picture?
Yep. And you'll see some of our other pictures as well through the lecture. All right. So self-promotion. So if you look at this galaxy, you can sort of see that there are like, you can't see any of the stars in this galaxy, but take my word for it that there are billions and billions of stars in this galaxy, just like our own Milky Way. And all of them are spaced apart from each other. So when someone like says, oh, like stars are like colliding or something, you have to be skeptical about that, because like you have to visualize stars are actually really small compared to the distances between the stars, if that makes any sense. So like the distance between stars in a galaxy is like most of a galaxy is actually empty space. This is quite important. Anytime you ever see something on the news about asteroid is going to make a near miss of the Earth, or stars will collide something, usually take that with a grain of salt, because what a near miss means in astronomy is very different from a near miss in any other context. And clickbait is a thing. So it looks like we have a question on the chat. Let's check this. Will you share how you take these photos? I'd be very interested in learning how to do that, possibly to pick up a new hobby. That sounds like a good discussion topic. Yeah, so basically the way we take these photos is we attach a camera onto our telescope and use a telescope as a camera lens. But we will go over that more in discussion if you guys are interested. Alternatively, I can write a Piazza post. So, and back to this galaxy real quick. If we're, let's say like this is the Milky Way Galaxy. The Milky Way Galaxy is about 100,000 light years in diameter. And so like the theme of all of this, as we've pointed out before, is that there's a lot of space between things in space. All that. So the nearest galaxy to the Milky Way is the Andromeda Galaxy. Do you happen to have a picture of that? Can you, the Andromeda Galaxy? Don't have a picture. Oh, okay, never mind. But yeah, you added it there. No, I don't know. Okay, yeah, okay. Yeah, it's the closest big galaxy to our own, and it's a full 2.5 million light years away. So this also means that the light we're looking at from the Andromeda Galaxy, it's actually visible in the naked eye. You can like go out in autumn pretty much, look up and like from dark enough skies, you'll be able to see like a fuzzy patch in the constellation Andromeda, as it were. And that's actually the Andromeda Galaxy. But you'd be seeing it as it was 2.5 million years ago, because it's that far away. And in fact, this picture of the Whirlpool Galaxy, we're seeing, I believe, about like 40 million, 60 million, 400. 23 million years ago. Okay. So this particular galaxy that you're seeing on screen right now is 23 million light years away, which means this picture is showing it as it was 23 million years ago. So I want you to think about one thing. As it turns out, people have measured and figured out that the Andromeda Galaxy, the closest galaxy to our own,
is on a collision course with the Milky Way. So in about like 5 billion years or so, these two galaxies will collide with each other. So if you can write on the chat, I want you to write on the chat what you think will happen when the Andromeda and the Milky Way galaxy collide. Do you think the solar system will be safe? Do you think the stars in the Milky Way will be safe? What do you think will happen? Stars will collide between stars in the Andromeda galaxy. So let's see, chat. Okay, so Imanol says, nothing, there's too much space between them. Some explosions, okay. I think the individual bodies will be fine because there's so much safe. So some explosions, well, yes, we would hope there would be some explosions, hopefully a little bit far away from our own solar system. As it turns out, oops, looks like I'm no longer sharing my video. Yeah, as it turns out, not much will happen because there's, as people have pointed out, there's so much space between everything. Both these galaxies are mostly empty space. So basically, we'll just end up with like a giant like super galaxy that just looks like a big blob. But nothing significant will happen to the stars inside the respective galaxies. There are some exceptions to that, and we may get to that later, but for the most part, this is the case. So good job, you all. So both the Milky Way and the Andromeda galaxy belong to the Virgo supercluster of galaxies, which contains about 100 such galaxies. And there are about 10 million such superclusters in our observable universe. And when we zoom out to very large scales, and Yonna's going to talk more about this in her next lecture, but when we zoom out to very large scales, we see that galaxies arrange themselves in beautiful filamentous structures. So on the largest scales of the universe is about the same in all locations and about the same in all directions. So this means that like the words that we use for this are homogeneous and isotropic. These aren't very important right now because Yonna is going to cover them later, but I want to point out that that on the largest scales of the universe is more like milk. It's not like boba. It's not chunky. Yeah. Okay, let's see if I can figure out this whiteboard situation. Ew. Sorry. Just use the touchscreen. Yeah, and I think I'll use the text. Okay. Let's say whole milk. No, actually, I'd say skim milk because there's not much in space. It's mostly just like empty space. Whole milk is like pretty like filled. Yeah. This is like 2% milk or something. It's like. Okay, Nicholas is all right. So the universe is homogeneous and isotropic, and these are both important words, but there is no need to remember them. So on that note, we will move on to the next part of Astro. So Shishir just basically mentioned. Oh, it's yucky.com/method. Yep. So Shishir just mentioned how the universe looks from the smallest scale, which is our Earth, all the way to the biggest things that we can see, which are these filamentous structures. And these structures are on the scale of the observable universe. So from the very small to the very big, Shishir just talked about everything. Now I'm going to talk about how the story of our own solar system is, how it formed, and how other systems form in a similar way. Okay, so how do things start? We have a galaxy, and inside this galaxy, if I can go back to the first slide, you might be able to see that there are little pink knots. Do you see those pink knots that I'm sort of like hovering over with my cursor? These are things in this galaxy that are called nebulae. They're clouds of gas and dust which are glowing as a result of stars that are illuminating them. So I'm now going to show you some pictures of nebulae in our own galaxy. Yes, please enable audio in the bottom left corner, and you should be able to hear things. So this is a nebula, and we also took this picture. So this is a very famous nebula. It's called the Great Orion Nebula. And it also turns out that this is a cloud of gas and dust, which is in our own galaxy. And it also turns out that this is it's what's called a star forming region. So in this galaxy you have, in this nebula you have sort of regions that are really dense, and inside of these regions of gas you start getting knots. The gravity is collapsing the gas into little knots, and when these knots condense, they start spinning. You remember the ice skater effect? We might have talked about this in classical mechanics. When you have the gas and it's coming inwards, it's like an ice skater with their arm outwards, and as they spin, they draw their arms inwards and they start to spin faster and faster, right? So as the knots condense over time due to gravity, they start spinning. And faster, the smaller they get, the knots. And as they spin, they sort of flatten out like a pancake, or like a pizza dough. Pizza is like the ideal analogy here. And the center of the knots gets really dense. So eventually the center of these knots becomes so dense that hydrogen atoms inside the center have enough energy to start fusing, have enough energy to regularly collide and start fusing. So when you have hydrogen atoms that are fusing together, you get a helium atom, and this starts a process called thermonuclear fusion. And what a star is essentially a thing which is fusing atoms and releasing energy in a process called thermonuclear fusion. So that's how a star is born. And so that's how. So. All right. Well, over time, these disks around these stars condense, but not all of the gas in these disks ends up going to the star, and sometimes there's leftover gas. And the leftover gas also forms clumps, but sometimes those clumps are not large enough to start fusion. So this is how you get planets like Jupiter or Saturn. They're sort of like failed stars in that they're what's left over after the star has been formed, but they're sort of clumps in their own right, but they don't have enough mass to actually start fusing. So meanwhile, if you have dust and solid material in these disks, and they start clumping due to gravity, the clumps sort of get larger and larger. You can think of it like a snowball effect. And eventually, the collisions will be fast enough, and you'll get larger and larger clumps, pebbles, boulders, and finally rocky planets. And now we actually don't know, astronomers don't really know how things go from dust grain size all the way to planet size. We vaguely know that we have pebbles, dust grain size things form into pebbles, which somehow wind up to the size of large rocks and boulders. And we think that they eventually end up forming into planets, but we're actually not sure how that process works exactly. It's an open problem. So this is another picture. It's of a cluster of stars. So it turns out if you have a lot of gas, like a nebula, and in your nebula you have like all of this gas, you're not likely to just form one star, you're likely to form a lot of stars. And so stars essentially form in these groups called open clusters. And so you have a bunch of these stars all in the same place that formed around the same time from the same gas. And these are called open clusters. And all of these open clusters are in our own galaxy. There are open clusters in other galaxies, but they're too far away, so we can't see them. So this picture, this is a really cool picture. It was taken by a telescope called ALMA, and it's a picture of the disk of dust and gas. So we've had the gas, it's spinning. We have this whole solar system, like this baby solar system, which is forming, and you have all of this dust and gas that's spinning, and it's flattened out into a sort of pizza dough shape. Now your question could be, what are these sort of gaps that you can see? Like you see that there are sort of dark gaps. As far as our understanding of planet formation goes, these gaps are actually little planets, rocky planets, which are clearing out the dust and gas from their immediate vicinity. As they orbit the star, in order to again, this is like an n-body problem from classical mechanics. In order to be able to orbit the star without being flung out, they sort of need to clear their immediate vicinity and either suck that material into themselves or eject it out of the system or out of their immediate vicinity. So we're actually getting these planets clearing out gaps. And this is really cool because we're actually able to zoom in on individual star forming systems, which are thousands of light years away. So from there, yeah, so our own solar system has like a diverse set of planets and moons. We're not going to get into too much detail about our own solar system today, but I'm going to at least like topically cover our solar system. So of course, the Earth orbits the sun, and we have the moon orbiting around the Earth, right? We're not the only planet with moons. As it turns out, the planets inward of us, Venus and Mercury, don't have any moons, but all of the planets outward of us have moons. Mars has 2 moons, Phobos and Deimos. Jupiter has tens of moons, actually. Potentially that number is in the hundreds now. Jupiter is so massive that it can contain a lot of mass. It can trap a lot of material in its sphere of influence, sort of. And so Jupiter and Saturn both have many moons apiece, and that is important to know because those moons are actually have pretty significant impacts on the rest of the solar system as well. And I think we're going to try, I'm not sure how the situation is with the coronavirus, but if this clears up, we are going to try to host some sort of star party on the roof of Campbell Hall. Basically what this entails is there's a observatory up there. We'll open the observatory up and point the telescope at different objects like planets potentially, and potentially other objects like in deeper space. And then we can if that ends up happening, we can talk about our solar system in greater detail, but I think for now we'll move on. So I'm going to go now into how stars work, as well as how they evolve over time. So I've already mentioned that what happens at the beginning of a star's life is you have a gas cloud that coalesces, and you have hydrogen inside this gas cloud that starts to fuse together, forming helium. So what happens after that? This is the area of astronomy and astrophysics called stellar astrophysics, and it's basically about studying how stars form and how they evolve. What we know is that after a star starts fusing hydrogen, it enters this really long state of rest, of quiet, at which the star essentially looks more or less the same. And depending on the mass of the star is something that's an intrinsic property of the star. Once a star is formed, it has a certain mass, and it keeps that mass more or less for its entire life. And depending on the mass of the star, stars' lifespans, their temperatures, and how they look at different points in their lifetime is very, very different. So what I'm going to show you next is a diagram. Let's see if I can find it. Where's your HR diagram? There we go. Okay, so this is a diagram. It's called an HR diagram that stands for Hertzsprung-Russell. And I think this is one of the most like information dense graphics in much of astronomy. It contains a lot of information and a lot of insights into how stars form and evolve in just one graph, in one plot. And their entire astronomy course is devoted to learning how to read this diagram. But we're hoping out of like this quick explanation that you're able to look at the diagram, you know what's on the axes, and you can sort of understand what it's plotting. Mm-hmm. Yeah. So again, I said that when a star is formed, it's able to like take a certain amount of mass from the surrounding gas cloud, and when the star is formed, it has a certain mass, and that mass sort of defines how the star looks at different points in its life. So on this diagram, you have your low mass stars that are sort of to the lower right, and you have your high mass stars that are sort of up here. Okay. So what happens when a star starts fusing hydrogen? When a star starts fusing hydrogen, it is stable for about anywhere from a few million years all the way to hundreds of billions of years, depending on the mass of the star. But the point is the star is stable. It's on something we call the main sequence. The main sequence is this line on the Hertzsprung-Russell diagram. So all the stars that lie along this line, we say they're on the main sequence. What that actually means is they have hydrogen and they're fueling themselves with hydrogen gas. So what was I going to say? Oh yeah, so what are the graph axes of the Hertzsprung-Russell diagram? On the y-axis, you have the luminosity of the star, and that's the brightness, how bright the star is intrinsically. And on the x-axis, you have the temperature of the star. Why are we plotting temperature and luminosity? Hopefully that will become clear, but essentially the mass of a star and it's the point at which it is on its evolutionary track determines how bright the star is, as well as how hot the star is. I want to point out real quick, there's something like very, very confusing that astronomers do on the HR diagram, and this is sort of now entrenched by convention, but it's important to note that, look here, it says decreasing temperature as you go rightwards on the graph, and increasing temperature as you go leftwards on the graph. So this is like very hard to sort of intuitize, but as you go rightwards on this graph, you're actually like reducing the in temperature. So this axis is reversed. So this means you can see this is colored, and it's colored according to the approximate color of the star that you actually see. So stars like this, stars that are cool and dim, they look red. So you might have remembered from our thermodynamics lecture, towards the end of the lecture, I mentioned something called black body, and how objects all glow, and they glow at different temperatures depending on how hot they are. The least massive, the smallest, least massive stars, we call those M-type stars. And they glow sort of red. And it's like you turn on your stove, it glows red hot. They're about that, and they're glowing red. As your stars get hotter and hotter, they start glowing yellow. So our sun is what's called a G-type star, and it glows like a good yellow color. That's the sun right there. Yeah. And as you get more and more massive stars, they're even hotter. They glow even more brightly. And so these are stars, if you go out into the night sky, you're familiar with certain stars like Sirius, which is the brightest star in the night sky. That's called an A-type star. These are pretty hot stars. It's an A-type. as you get even hotter, you get certain types of stars called O or B type stars. These are the hottest, the brightest types of stars. They're also the most massive. And so the most massive types of stars have the most gas, the most fuel, but they also burn through that fuel the fastest. In fact, they burn through it so quickly that sometimes they only live for a few million years. And on the scale of the universe, that's a really, really short time. So these are the most massive stars, and they're really burning through their fuel. They're here for a good life, not a long life, I guess. So if you've ever gone out at night and you've seen stars like Bellatrix in Orion, like Spica, I forget which constellation that is in. Yeah, but these are the hottest types of stars. Another thing of note.
And I should quickly mention the stars on the bottom end of this. These are cool. These are dim stars and the red stars. They literally last so long that some of these stars have been around since the beginning of the universe as we know it. And so, like, close to the beginning. Yeah, like they live like 13 or 14 billion years, and that's about the age of the universe. So they literally like, what's that? Yeah. So like all the way up to some like stars are sort of like that. Yeah, that's true.
So all of those stars, like they haven't really died yet because they will last longer than the current age of the universe is. So they haven't really died. Yeah, not a single red dwarf has ever died, Nicholas says, and that is true because their ages, they live for really, really long times. And our universe itself is not old enough to where even if one formed at the beginning of the universe, they still would be living. Yeah, and towards the lower end of the scale, even if you waited 100 times longer than the universe has existed so far, they'd still be living. So they really don't die. So you can think of like these low mass stars as like hybrids. They don't or like electric vehicles. I don't know. Like they don't take a lot of fuel, but they're also really efficient in their use of it, and they last a long time. There's a question. Are these types of stars capable of having planets?
We'll get to it in a bit.
Wonderful question. It turns out that our professor, our research advisor professor's whole research is on this topic. But we will get to this. So just hold on for a second. Another thing of note, on this diagram again shows you, this is the main sequence where stars are fusing hydrogen. When a star of a certain mass sort of lands on this diagram, as long as it has hydrogen, it stays in the same spot. When it runs out of hydrogen, some interesting things happen. The star will start changing in temperature and luminosity, and it'll sort of move around on this diagram. So that's the process of stellar evolution. Once stars die, their remnants have sort of, they leave sort of remnants, and these remnants can be very hot, but very low luminosity, and so these are called white dwarfs. Also, when a star has run out of hydrogen but still has other things like helium and carbon and heavier elements, we would call those supergiants and giants.
It's important to know how stars die. So when a star reaches the end of its lifespan, basically it's finished fusing hydrogen into helium. Stars like our sun, what happened to stars like our sun is that at some point they begin to fuse like elements down the periodic table, right? And they lose their equilibrium. Stars are always in an equilibrium between the gravity that's pulling them inwards, that's basically trying to collapse them, and the pressure and heat that's pushing against that.
When we look at a star, it's a sphere, right? You look at the sun, it's a sphere. Why is it a sphere? Because the sun is always in this balance between gravity that's pulling it inwards and the light and the energy that's due to the fusion of hydrogen that's pushing the star outward.
So as you might imagine when the fusion changes, the amount of energy it's putting out changes, and this equilibrium will change as well. So what happens to stars like our sun as in another 4 or 5 billion years is that they will move off the main sequence and they'll start to puff out. They'll become cooler and they'll puff out. And they'll turn into something that's called a red giant. So there are examples of these kinds of stars in our night sky as well, like the star Aldebaran and the star Betelgeuse. Some of you might have heard like, these are, in general, they're called giant stars. But stars like our sun will, once they become giants, they'll sort of just like, eventually they'll just puff out their outer layer, their outer envelope will move outwards, and we call that a planetary nebula. Let me see if I can pull up an image of a planetary nebula somewhat. All right. So this is how stars across all temperatures, all masses look. But I still haven't given you a good perspective of what kinds of stars are actually out there. Can I get any guesses for what the most common type of star is? Do you think the most common type of star is on this side of the Hertzsprung-Russell diagram, or on this side? If you have any answers, please, or guesses, please write it on the chat. Kate says that she feels like it's on the right side. That's generally right. Yes. So by far the most common types of stars in our galaxy are the stars on the right. These really cool red dwarf stars. They're way more common than the stars on the left side. The really massive stars are very rare. But if you look out into the sky, you go out tonight, you look up, most of the stars you see in the sky are this type, are generally in this region of the HR diagram. Any guesses for why that is? Do they seem rare? Possibly because they burn fuel so quickly. Yes, that is part of the reason. It's because they don't last for very long. Also, we talked about how like stars form, right, from their clouds of gas. It's just more common for smaller stars to form than it is for a region, a knot, to become so big that it just like it has 10 times or more the mass of the sun. Mm-hmm. Some of the stars at the highest, you can sort of see over here, it's saying like, we think the largest stars in existence are about 60 to 100 times the mass of the sun. Any larger than that, then and stars will literally blow themselves apart because they can't maintain that equilibrium. So we think 60 to 100 masses is about just as massive as a star can get. Mm-hmm. So and the reason why when you go out and you look up and you see stars, it's bias. It's called Malmquist bias, and this is a really important bias in astronomy. And Evan seemed to be pointing out. Yeah. And the reason is, if you go out and look out at the night sky, there are tons of these M dwarf stars which are out there. They're just really dim and they're faint. And when you actually look up into the sky, you can't really see them. But a star like Spica or Bellatrix, even if it's really rare, that means most of the stars that are this bright are very distant because they're just really rare. So it's not likely that you'll see one really close by. But even if they're more distant, they're just so bright that they're easily visible to the unaided eye. So that's why it's a bias whereby dim stars appear like they're less common because they're just harder to observe. So this is called Malmquist bias, and this shows up all over astronomy. Bias in which something that's harder to observe seems like it's less common. It might not actually be less common, it's just harder to see. Last thing I want to point out before we move on is we talked about the depth of stars like our sun. It's also important how stars are much more massive than our sun die. So even though they're rare, they die spectacularly. And so stars that are like about, I think, 8 solar masses and above go out with a bang, literally. So these kinds of stars, when they reach the end of their lifetime, there's a
they start to fuse hydrogen into helium and heavier elements. Eventually, they get to the element iron. And then, as it turns out, iron creates less energy. Fusing iron creates less energy than it takes to actually fuse the elements together. And so now you're basically, the net amount of energy you're generating through fusion is negative, right? And this is catastrophic. This means that all of a sudden there's no equilibrium anymore between the gravity pulling in and the fusion pushing out, because there's no fusion pushing out. There's nothing pushing the star outwards anymore, and there's still gravity pulling it inwards. Mm-hmm. So within a fraction of a second, and remember, these stars have lasted for tens of millions of years, within a fraction of a second, when the star hits iron, it just collapses. And when it collapses, the energy from the collapse is so great that it rebounds. And this is what we call a supernova. Do we have okay. Well, supernovae are some of the most energetic events in the universe. For a brief period of time, a supernova, when it explodes, will outshine the whole galaxy it's in. So again, if I'm going back to the slide with a galaxy, sorry, this one. This galaxy has hundreds of billions of stars in it. And briefly, a supernova can outshine the entire galaxy it's in.
I can try showing you one on this, but you can sort of see my phone screen. You can see an arrow pointing to something on that. And that's actually a supernova. Yeah. And so you can see, like, the supernova is comparable in brightness to the entire galaxy. And these supernovae last for like only a couple of weeks or so. But they're visible from like across space, and they're very important in astronomy as well. So we'll cover that in more detail slightly farther down this lecture. All right, so now I'm going to ask you, we're going to move on to the next part. I'm going to ask you a question. And you can just sort of, one thing to mention real quick. Some of you might have heard on the news recently. Ooh, thank you. Some of you might have seen on the news recently that the star Betelgeuse is behaving very strangely and might go supernova, right? So what does this all mean? Basically, if you look up in the night sky in the constellation Orion, the shoulder of Orion is the star Betelgeuse. It's well known to be a red giant. And if you go back to the Hertzsprung-Russell diagram real quick, we're at the Hertzsprung-Russell diagram. This kind of star is right. Oh, Betelgeuse is actually listed here, right? It's already moved off the main sequence. It's become a supergiant, and it's one of the more massive stars in existence. So what happens to Betelgeuse when it runs out of fuel? We don't think this is going to happen immediately. We think it might be on order 1,000 years or more before Betelgeuse actually goes supernova. Could be 100,000 years. Anytime in the next 100,000 years. Yeah. But when it does go supernova, what's going to happen is, like in a matter of seconds, it'll collapse down and then rebound. So if you're looking in the night sky, you'll basically see Betelgeuse wink out and then become really, really, really bright. In fact, it'll become so bright, it'll outshine Venus, certainly. And it might outshine the moon. We don't know because we've never seen a supernova this up close before, but it might be anywhere from as like bright as Venus to as bright as the moon. It'll almost certainly be visible during the daytime. It'll cast shadows during the nighttime, very bright shadows too. And it'll be like a pretty extraordinary event. But at the distance Betelgeuse is to us, it won't be harmful to us. So a lot of astronomers really want to see Betelgeuse go supernova because it would be like a really extraordinary event to see in the night sky. Okay, hold on. So we have some questions. I might have missed this, but why can Betelgeuse be large and red? Keyword being large. I might be associating red stars with being smaller. Great question. Red stars are smaller, but those are red stars on what we call the main sequence. Oh, sorry. We should disambiguate large and small for massive and less massive. Stars that are on this area of the main sequence are not massive. So they aren't very heavy. stars like Betelgeuse are extremely heavy, and therefore they're very large in size as well. Yeah. So again, to recap, we have something called a main sequence, right? So as long as stars have hydrogen, they will follow this neat line, right? Where the less massive stars are on the right and the heavier stars are on the left. The moment the stars run out of hydrogen, like all of these bets are off. They just sort of move around on the diagram, and they can be blue, they can be red, they can be like whatever they want to be. There is a science to this. They definitely follow certain rules, but basically Betelgeuse is a very heavy star that has run out of hydrogen, and as a result has sort of puffed out, cooled down, and because they're really cool, because Betelgeuse is really cool, also really red. So remember that the color of a star indicates how hot it is, right? Cooler stars would be redder, and hotter stars will be bluer. Okay, so someone asked for how long Betelgeuse will be this bright. I think it's anywhere between like weeks and months. So it's sort of hard to it's bright really quickly and then slowly fades out over the span of like months. But yeah, for about like a month, it'll be extremely bright in the night sky. Yeah. And I forgot to mention, this has actually happened before. None of us will remember it, but the Crab Nebula supernova exploded in 1054 AD, if I remember correctly. So ancient civilizations, such as the Chinese, recorded quote-unquote guest star in the night sky. They recorded something very, very bright, and there actually was a star right above Orion before 1054 AD, and that star went supernova. And for some time, a lot of different ancient civilizations recorded a very, very bright star suddenly appearing in the sky, and this was actually a supernova. All right, so in the interest of time, I would love to discuss this all day, but in the interest of time, I'm going to move on to the next section, which is I think this is like stepping back from what's actually in the universe to how we study the universe. So again, astronomers are not like other scientists. We're not like biologists in that we can't go out into a lab and like tweak stuff and grow stuff on a petri dish. Astronomy is what we call an observational science, right? All we can do to learn about what's in space is observe it. When you go out and you look up into the night sky, you see light from the stars that is coming from perhaps thousands of light years away, sometimes hundreds of thousands of light years away, and is entering your eye. So astronomers have nothing except that to figure out what's in space. So how do we do it? How does that actually work? For this, again, remember that we have nothing but light. So I'm going to ask you a question, and I'd like everyone, if you can, to write on the chat. If you can think of any properties of light that we might be able to exploit to study what's actually out there in space. Think about properties of light. What have we learned? Constant speed. Okay, speed. That is one property. Okay, so now we're getting someone saying color. I'm looking more at something like that. The color of light is a good one. Luminosity, there's a good one as well. The bending of light. How do we know that light is bending? You're on the right track. How do we know that it's bending? Someone said frequency as well. This is a good point. Frequency is actually the same as color for light. You might remember this from the E&M lecture. If you know the frequency of light, you know the color of light. Mm-hmm. So we'll count those two as the same thing. So the two answers have been that I'm sort of looking towards are color and luminosity. More accurately, color and brightness. Those are two things that we can just go out and just measure about what we see, right? We can't really measure gravity directly. We can't measure the bending directly, but we have ways of measuring that. But I'm just looking at things that we are able to measure directly. These are the shape of brightness. So we'll count this the same as luminosity. Someone's on to something here, but yes, like and we'll cover this pretty soon, but we'll count that under luminosity. There's still some more properties. I'm in the interest of time, I'm going to go straight to what those properties are. Hold on. Oh, oops. It's like let me unhide this. I can't hide it. What did you do? Okay. You can present from here. You should present from here. Actually. Don't skip. Don't skip. Yeah. Okay. So I'm gonna present from here. Let's try this. Is this working? Yeah. Yeah. We're just like. Hold on. Where is screen sharing? Yep. And screen share. Got it. All right. So take two. So what are the properties of light? So what are the properties of light? Position. So this is something, if we go out and we look at a star, what we can measure directly is where it is on the sky. That's the position of the star. We can measure its brightness. How bright does it appear to us? So I believe, Angel, I'm not sure how to pronounce that, got that right. We can measure the color of the star. Is it red or is it blue? And the last one is one that I didn't really expect anyone to get. It's a bit tricky. It's called polarization. So the polarization, if you remember, light is a wave. The wave can be waving in a vertical direction or a horizontal direction or a combination of the two. And polarization is sort of the direction of the waviness. Okay. And so if you've ever seen a 3D movie, that's how 3D movies actually work. They work based on polarizing the light differently. So these are the things we can directly measure about things in space. So now we're going to go over if we can actually quantify these different properties of light. This is literally how astronomers do everything. We measure position over time, we measure brightness over time, we measure the color over time, and we quantify all of these using our telescopes to try to understand what's out there in space. So, and the last one. Some of you might remember from I talked about one thing that's not light. So in pretty much all of, there's a couple exceptions, but the most significant one right now is astronomers are now using gravitational waves to study the universe. And I believe this is really cool because entirely in the history of astronomy, it's been us using the light to study the universe. And gravitational waves represent the first, mostly, there are exceptions to this, but pretty much the first thing that's not light that we're using in order to study the universe. And so it's almost like our ears suddenly open to the universe as well as our eyes, right? So that's why gravitational waves are cool. So now let's go over each property and see like how we study them. So for position, the thing that we're studying, or like the study of position in astronomy is called astrometry. And this is really confusing with astronomy, but it's different. Astrometry, astro is the prefix for star, metry is to measure, so we're measuring the position of stars. We can use astrometry in order to figure out like where stars are, as someone pointed out, whether light is bending around things, right? Whether stars are like moving around. For example, we have a video in the slide. Go to that real quick. Screen. Or oh yeah. So we showed this during the DR lecture. Some of you might remember it. Oops, it looks like is it lagging for you guys? Okay, yeah. We will send this in the chat actually. I can share the link. Yeah. And send it in the chat. And but in the meantime, so astrometry is the measure of stars' positions over time, and it's a pretty useful technique. So right now, what we're looking at here is stars like whizzing around the black hole in the center of our galaxy. So there's So we don't see anything other than stars like whipping around here. When we send this in the chat, you'll be able to see that they're really like whizzing around something, and we don't really see anything there, right? But we can use astrometry to measure exactly what their paths are, and then we can use math to figure out how fast are they going, and based on how fast they're going, you can deduce what the mass of the object that we can't see there is. And as it turns out, it's like millions of times the mass of the sun. So what could be a million times the mass of the sun and not glow at all, like basically not show up at all? And it turns out that's a black hole, right? So that's how we figured out that there's a black hole at the center of our galaxy, among other ways. So, and also it's important to know if we're seeing something move really quickly across the sky, chances are generally it's closer to us. If you've ever been in a car, like driving down the highway, the stuff really near to you moves really quickly relative to you. It looks like it's moving really quickly. The mountains look like they're moving really slowly. So using this effect, usually if we see something moving really fast, it's usually asteroids, because asteroids are pretty close to us. They're in our solar system. And so sometimes we'll be observing something and we'll see something zoom by. And those are usually asteroids. And in fact, you can discover asteroids. What is that effect called? Which effect? Oh, it's not quite an effect. I would say it's more, we'll cover something similar to this in a bit. But the effect you're thinking about is called parallax. And that is a real effect too. We will try to cover that. We are running out of time. But, we will try to cover that. So for now, I will move on to the next form of light. And for this, I'm going to go to our whiteboard again, and hopefully this will work. Okay, so the next type of light observing method is called photometry. What is photometry? Photometry is the measure of brightness. And in my opinion, photometry is one of the single most important revolutions in astrophysics. It is what allowed us to go from not really knowing anything about how things work to knowing a lot about how things work. So what do we actually learn when we measure the brightness of something? Not very much. But what happens when we measure the brightness of something over time? Some very, very interesting things happen. I'm going to draw something called a light curve. Move this over here. So a light curve is a graph of brightness. Ignore the 3 S's there. Versus, oh shit. Versus time. So, dang, I'm sorry. So let's say we're observing a star and we see that it's changing in brightness. Oops. The ways in which a star changes in brightness are crucial to being able to find out how the star works and how it changes in brightness. So there are certain kinds of stars that when we observe the brightness over time, they look like this. They're sort of sine wave, sinusoidal, pulsation-y changes in brightness. And when we look at their color and their temperature on the HR diagram, we see that they sort of all fall in a certain strip along the HR diagram called the instability strip. So this is interesting. These stars are called variable stars, and they pulsate in brightness over time. And the reasons for that are very interesting. It's because the hydrogen gas inside of them sort of becomes more opaque and less opaque. And so these stars are sort of unstable. But they're also very useful for reasons Shishir will mention later. What else can we do by looking at the brightness of a star?
what if we look at the brightness of a star, oops, and we instead see something that looks like this? A graph like this, if we look at a star and we see the brightness changing like this is called an eclipsing binary. So what this is it's actually two stars which are orbiting around each other, and as they orbit, one of the stars will pass in front of the other star and will block some of that star's light. And when we see that, we see a dip in brightness. And so based on the time of these dips occur, as well as how deep dips are in brightness, we can learn all about the properties of the two stars, including their mass. Using orbital mechanics, we work out the math and we can figure out exactly how massive the stars are, exactly how big the stars are. We can find out so much about stars by observing these stars. They're called eclipsing binaries. And my favorite thing about photometry, let's say you're observing a star. Oops. Oh no, oh no. I need my brightness. There we go. All right. And brightness that looks like, oh, I can't draw. No. And let's say this is like this kind of a pattern of dip in brightness is due to what we call exoplanets. So you go out into the night sky. Our solar system has 8 planets. Surely other stars also have planets. This fact was not known until 1995. In 1995, the very first planet that was observed around a star other than our sun was discovered. And when these planets orbit around stars, sometimes they'll block the light from their star, and every time they orbit, they will block the light from the star and we'll see a dip in brightness. And based on the shape, size of the dip in brightness, as well as how long the time takes, if we have an Earth-sized planet that's transiting around a star like the sun, the time between these dips in brightness will be 1 year. Does that make sense?
Around every year,
right? So
you can even tell what a year on that planet would be. And from that, Kepler's laws of motion will tell you how far away that planet is from the star. There's a whole host of things you can find out using this method, and we're hoping to cover that in a full discussion section. So,
yeah, so this is also what me and Shishir do for our research. It's mostly investigating planets using this method, photometry.
Planets do exist around all kinds of stars, and yes.
And they do exist around the cooler, redder stars as well. The last thing, oh my God, if we see like a supernova or something, we can also, let's say we see a star that goes from being really dim to like suddenly being really bright, and then it looks like this. We can tell how the star looked before it went supernova. We can tell why the supernova happened, and we can tell a whole host of things from the supernova. So this is all a technique called photometry. Oops. All right. With that,
one more technique that astronomers use to study stars and the night sky, and that's called spectroscopy. They basically leverage the property of color. They study color in really great detail in order to figure out what's going on in space. I'm going to quickly describe to you how exactly that's done. So in spectroscopy, we take the light from a star and split it into a rainbow.
So yeah, you can go out into the night sky and you can see a star and it looks red or it looks blue, but how do you actually quantify what the color of a star is?
So you split it up into a rainbow, and you can basically take a picture of that rainbow. What you'll notice is that like the rainbow will have like dark bands in it, and that's actually sort of like a barcode. The reason why this is a thing is because it has to do with the electrons in the orbitals of atoms jumping energy levels. And so I think we'll cover this more in quantum mechanics. But right now I'm going to sort of explain it by saying these are called emission and absorption lines. And they are a chemical barcode for what like chemical composition you're looking at. So for example, if we're looking at a neon lamps have neon in them and then neon glows, right? If you split that light into a rainbow, you'll notice like a distinct barcode-like pattern. And that barcode pattern basically is like a fingerprint that tells us, okay, there's neon there. And when we do this for stars, we can see everything that a star is composed of. We can see the hydrogen, we can see the helium, and we can see the other trace elements that are on a star. And this turns out to be very, very important. As it turns out, as telescopes get better and better, we can even do this on planets. We can figure out what chemical elements are in the atmospheres of planets. So Mike is asking a good question. What if there are stars we can't see because we can't see that color, like ultraviolet? Question. Well, until the 1800s, astronomers would just like, we're kind of done. They just went out and they looked up, and that's all they knew about space. Now we have telescopes, and in fact, we don't even look through the telescopes anymore. We put cameras on the telescopes, and the cameras collect data. And using this data, we can quantify things like position, brightness, color. In fact, like our research entails like using these images from a camera and then using like computer programming to analyze these images, collect data from those images. Like it's all about using computers and using like all of the like technology available to us in order to make measurements rather than just looking through. So if there are stars that we can't see, or there aren't quite stars that we can't see, but there are things that we can't see, like infrared or ultraviolet or X-rays. There are a lot of such phenomena. And in those cases, we use different kinds of detectors to detect them. We use different kinds of cameras that are sensitive to that light. So just like thermal cameras can see infrared, we also have cameras that can see in ultraviolet. Ooh, what about Planet 9 in our solar system? We don't know. Jury's out on that one. But that's it. That's it. Might exist. It might not. And so, oh yeah. And the other thing that I wanted to mention really quickly is the Doppler effect. So, if any of you have like heard an ambulance passing by you, you know how it goes. Like it's high pitched as it's coming towards you, and then as it goes away from you, the siren goes like low pitched, right? So this is an example of the Doppler effect. Sound is a wave, and when the ambulance is moving towards you, the wave is compressed because the ambulance is moving, right? When the ambulance is going away from you, the wave is expanded out, and that causes the pitch to shift down, right? And the same is true of light, as it turns out. Light is also a wave, and it's also traveling at a constant speed. And so this means that when something is moving towards you, its light will be ever so slightly bluer. When something's moving away from you, its light will be ever so slightly redder. And you can actually use this to figure out whether things are moving towards or away from you. Just to recap this entire section, we've just by looking at the position, brightness, color, polarization of light, we've learned about the masses of objects, the temperatures of objects, the velocities, the positions. We learned all of this about space. So this is how we pretty much figure out everything in astronomy. The last thing I want to mention is when you look up into the night sky, you see like a bunch of stars, but
we haven't really covered how we know how far away those are, right? We've covered like all of the scales of the universe, but we haven't covered how we know that. Like how do we even know that we're not on a flat Earth and like all the stars are just like on a like dome above us and they're all like at the same distance? How do we know how distant things are in space? This is a really good question. And this is what we call the distance ladder. So the distance ladder is a way of like going from really small distances up to really big distances, to sort of like calibrate every measurement. So this is sort of like, let's say you wanted to measure distances. You start off by like measuring like a centimeter. You have like a ruler, right? And you can like, if I wanted to know the distance to Paris, like I start off with a ruler, right? I know like the distance of like the smallest scale. And then I use that ruler to measure out a kilometer. And now I have something that tells me how large a kilometer is. Now I use those kilometers to extend out all the way down into like Paris or whatever and figure out like how far away Paris is that way. So in the same way, we can at the smallest scales we have parallax. So if you extend out your finger in front of you like this, right? Look at the background. Close one eye and look at the background, right? And then open this eye and close the other eye. Sort of like switch the eye that you're looking at. You'll notice that your finger sort of switches, right? It moves in relative to the background, right? So this is actually exactly what, if I can draw on here real quick, right? This is very similar to what happens in our night sky. So let's say we're looking at a foreground star and something distant in the background. So you have your sun here and you have your Earth going around your sun, right? So at one point the Earth is over here and the other point the Earth is over here. This is separated apart by 6 months where the Earth is in its orbit. Does that make sense? And there's a star here, right? When Earth is on one side of its orbit, we're looking at it like this, and when it's on the other side of its orbit, we're looking at it like this, right? So relative to the background of the stars, right, the background like being somewhere back here, we're seeing the star shift as the Earth moves in its orbit. We see that as a wobble. Yeah, so stars like closer to us will actually like wobble as the Earth orbits around the Earth. And this is a really, really, really subtle effect. But as it turns out, nowadays astronomers are able to measure this effect. And this can tell us the distances to things in our galaxy that are relatively nearby in our galaxy. So there's a spacecraft called Gaia. It is essentially measured, oh my gosh, the distances of billions of stars in this way by measuring the quote-unquote parallax effect. In the interest of time, we should move on to the next. So parallax is how we measure things really close to us. Like in our solar system, maybe 100 light years away, at the very max, 1,000 light years away. This is how we measure the distances to those objects. This is a lot of the stars in our Milky Way. So the next level up is, what if something is in another galaxy, but like a really nearby galaxy? How do we measure its distance? How do we know that other galaxies are even separate from our own galaxy? How do we not know that these fuzzy patches in the night sky are in our galaxy? As it turns out, there is an astronomer named Edwin Hubble who made a measurement of a special kind of variable star in our closest galaxy, the Andromeda galaxy. And he figured out that that in this kind of star, it pulsates, but its pulsation pattern will tell you how fast it's pulsating, will tell you exactly how much light it's putting out, right? So the challenge in astronomy is like the analogy sort of, let's say you have like a bicycle headlamp and a semi-truck headlamp, right? If the semi-truck is really far away and the bicycle is really close to you, like based on the headlamps will look around the same brightness, right? Because the semi-truck is really far away and the bicycle is really close to you. So how do you know that you're looking at a semi-truck versus a bicycle, right? And the answer is, if I know that the headlamp of the bicycle is 50 watts, if I know exactly how much light it's putting out, I can then calculate, okay, if it's a 50-watt bulb, that's not all that bright. So what we're looking at must be relatively close to us, right? And this is the same thing we do here. So for these Cepheid variables, this is a special kind of star called a standard candle. And that's a very important name. So again, remember back to the photometry section, we talked about light curves. It turns out that these stars pulsate in such a way so as to basically how long they take to pulsate is related to how bright they are intrinsically. So centipedes are an example of a standard candle, and so we can calculate exactly how much light they're putting out, and therefore how far away they are. Edwin Hubble did this to measure the distance to the nearest galaxy, Andromeda, and it was able to figure out that it was about 2 million light years away, way too distant to be in our own galaxy, and so therefore he inferred that it was an entirely separate galaxy. As it turns out, a certain kind of supernova is also a very important standard candle, and this is very important as well. Finally, we've noticed, I talked briefly about the Doppler shift. Things moving away from us are redder, right? As it turns out, people noticed that almost nearly every single galaxy, with the exception of like 2 galaxies, I think, are red shifted. So they're redder than we expect them to be. And people figured out pretty quickly why this was. It's because the universe is expanding. The universe is expanding so much so, in fact, that over large scales, like the distances between galaxies, all of the galaxies, everything in the universe is receding away from us. It's getting farther and farther, like it's moving away from us. So when we look at the color, because of the Doppler shift, these galaxies, as they're moving away from us, end up redder than we expect them to be. As you get farther and farther away from us, like if you have like something way farther from us, will be receding much faster. The best way to think about this, in my opinion, I don't know if you can see video here, but Yonna has kindly baked us some chocolate bread. You can think of banana. Oh, is it banana? Okay, but it has chocolate chips in it. Yes. Okay, so it has chocolate chips in it. When you bake the bread, it rises, right? And so you can think of the chocolate chips in this bread as being the different galaxies in our universe, and the rising of the bread is like the expansion of the universe. Even though there's no like one center of the universe, all of the chocolate chips will eventually get farther away from each other as the bread rises. They're not expanding away from a point, but they're in general expanding away from each other. Right? Mm-hmm. And if you think about it enough, you'll figure out that a chocolate chip at the ends of the bread will get farther away from each other than chocolate chips that are right next to each other, right? And so this is to say that if we're looking at a galaxy that's really distant, we expect its light to be way more redshifted. We expect it to be way redder. Galaxies that are like way in the background of space are so redshifted that like ultraviolet or like even more like energetic light gets shifted all the way into the red part of the spectrum. And so like these are galaxies that are very distant to us are very redshifted. So one of our other hobbies is looking through telescopes, and we have actually looked through a telescope. The farthest object we've ever actually seen with our own eyes, me and Shishir, is a quasar. And that quasar is 12 billion light years away. It's so distant that it looks like it's receding from us so quickly that its light has been shifted from ultraviolet to visible, which means when we looked through that telescope and we saw this sort of faint red dot, we were actually seeing ultraviolet light. So in a way, that's like the one way that you can actually see the invisible types of light. They're actually redshifted so much that they're redshifted into the visible part of the spectrum. So that's, as it turns out, everything we've covered in this lecture comprises only some like small fraction of the observable universe. Astronomers now think there's this really other strange thing that we don't really know very much about called dark matter. And there's another really strange thing called dark energy. And we won't have time to cover this today, but we're hoping to cover this in our section along with exoplanets. So yep, we'll tell you when that happens because of this coronavirus situation. Thank you all for tuning in. That's about it for today. Make sure you fill out the attendance forms, and you're all free to go now. That was it. See you guys. And feel free to ask questions. We're here to stay. Any last questions? Bye. Email us. No.
do we see the space videos?
Yeah.
I think Nicholas watches them. Yeah, I watched some too as well. But if you have a question about that, you're more than welcome to ask us. Different answer. Looks like I have more stuff to watch. Yeah, go ahead.
Wait, I just unmuted myself.
Yep.
If I saw something when I was watching a video, and it was talking about how if a planet orbits very closely to a sun or a star due to the mass and energy, then it will become locked, where it will have continuous day and continuous night.
Yep.
Why do you know why that is by chance?
Yes.
Yeah.
So
Why does the moon only present one side?
you might have heard like the moon has a far side and a near side. We've actually never, like, if you look up at the moon, you've actually never seen the back side of the moon, and you will never, because it's actually also it's locked to the Earth in the same way. Share screen, whiteboard, share. All right.
All right. So the reason why this happens is because you have something like the sun, right? Or it really doesn't matter what you have here. You can have the Earth or the sun. You have another object, right? It could be the moon or a planet, right? Gravity gets stronger the closer it is to something, right? And so that means the front of this planet has a bigger gravitational pull than the back, right? Or if I'm to redraw this real quick, slightly larger. Right, so the front of this has a bigger gravitational pull than the back, right? And this means that, like, if you can visualize it, that means that this side will basically get pulled on with greater force, and therefore it'll always like point towards this, and it'll basically spin itself such that no matter where it is in its orbit, this side will always be pulled more strongly, and therefore it'll only present like that side. So if this is a star, and this is like the companion planet, the front side will like be pulled more strongly, and that's what causes like tides on the Earth and stuff. The reason why this doesn't happen for more distant planets is as the planet gets farther and farther away from the star, like this distance, the radius of the planet becomes completely insignificant compared to the distance it's orbiting to the star, right? And so the difference between the force from the backside and front side of the planet becomes insignificant as well, and therefore the tides really don't matter as much, right? But for stars or for planets that are orbiting really, really close to their host stars, this is a really, really significant effect.
That makes sense. Thank you.
Yeah. All right. No more questions. Then we will find out. Emil, are you sticking around to ask a question or any other questions? I think that seems to be it. Yeah. Let's see. Oops, yeah. How do you leave? Stop share. No, not stop share.
Isn't there X in the top?
End meeting.
End meeting.
Oof, that was a bit inefficient.